Okay, I want to talk about one more example of a first order differential equation application. And that's mixing problems, which is of interest to for people that are into like fluid chemistry or water chemistry. Let me show you what I'm talking about here. So yeah, rather than trying to talk about this in full generality, I would just rather focus on a particular example and then talk about some general principles from that. So here we have a tank that contains 8 liters of water, into which is dissolved 32 grams of salt. So this is a saltwater solution. The salt is the solute. The solution is the salt together with the water. Um, Into this tank is being pumped in more salt water. But the concentration of this salt water is perhaps different. It's 2 grams per liter. If you look at what's up here, we have 32 grams of salt being dissolved into 8 liters of water. So the concentration of that salt water initially is 4 grams per liter, right? 32 divided by 8. But we are pumping in salt water with a lower concentration, and it's being pumped in at a rate of 4 liters per minute. Okay. And then we have well mixed solution flowing out of the tank at the same rate, 4 liters per minute. So the same amount going in is the same amount the amount of solution going in is the same as the amount of solution going out. Okay. Well, we want to figure out from this. Maybe I'll ask the question here in blue. What is S of t? The amount of salt in the tank at time t. Okay, that's the question before us. What is the amount of salt in the tank at time t? Okay, well, we're going to try to set up an initial value problem to solve this particular problem. First, we're going to write down a differential equation. So, key principle, key idea is that if you want to know the rate at which the rate of change of something, so in particular ds dt in this case, if we want to know the rate of change of the amount of salt present in the tank, then we should measure the rate at which salt is entering the tank okay, minus the rate of which the salt is leaving the tank. I think this is very sensible, right? The rate of salt entering the tank is going to contribute positively to the rate of change of the salt in the tank. But of course, this is going to be sort of mitigated by the rate at which salt is leaving the tank. All right. Good. So this is the key idea for this problem, and this is the one that will generalize to other situations which we may see in the future. Well, what is the rate at which salt is entering the tank? So you know what? Before we go too far, let's just draw ourselves a picture of what's happening here. We've got a tank here. This is my conception of what a tank looks like. Forgive me. We've got water, salt water, sitting inside of this tank. And this salt water, well, yeah, it is what it is. It's got S of t units of salt, grams of salt. I don't know why I'm saying units of salt. It's got S of t grams of salt inside there. And we have stuff entering from maybe a pipe. You can imagine a pipe is dropping fluid into this thing. and it's doing so at a rate of 4 liters per minute. And it has a particular concentration. It has a concentration of 2 grams per liter. All I'm doing is reading from the problem. I'm not doing any math. Okay? But then we have an output spigot. Okay? We have stuff leaving the tank. And it's leaving the tank at the same rate that it's entering. So we have 4 liters per minute of well-mixed solution leaving the tank. But crucially, what is the concentration of the fluid leaving the tank? So concentration, remember, is the amount of solute present divided by the volume of solution. So this is going to be equal to the amount of solute divided by the volume. First of all, what is the amount of solute present? Well, it's S of t, right? That's the amount of salt present at time t. So this is going to be S of t, that's the amount of salt present, divided by the amount of solution. Now, we should think, what is the volume of solution in this tank? Well, there are 8 liters initially in the tank. And notice that the amount of solution entering is the same as the amount of solution leaving. So, in other words, using this exact same idea, we can kind of say like dV dt, if V is the volume of solution, is 0. So V is constant. In other words, it's 8. This probably agrees with your intuition as well. Okay? So then using this key idea, what we can write down based on this picture here, what is the rate at which salt is entering the tank? Well, it's entering the tank at, so its concentration is 2 grams per liter, and it's entering at 4 liters per minute. So the amount entering the tank is 8 grams per minute. The rate at which salt is entering the tank is 8 grams per minute. And what is the rate at which salt is leaving the tank? Well, that's S of t divided by 8. That's the concentration times the volume, which is 4. And again, the units on this, I don't know why I'm writing the units out, but it's grams per minute. So that massaging this, we get the equation. Let me write it down here in the end. ds dt, and I'll suppress units for real now. I get 8 minus s divided by 2. That's my differential equation. Okay? And what I want to alert you of is that this is separable. Okay? It's separable. So let's solve it. Oh, maybe I should say one other thing. We can say something about initial conditions, right? Here's our dE. We can also say something about the initial conditions. What is S of 0? What is the amount of salt present in the tank at time t equal to 0? It is 32 grams of salt. So S of 0 is 32 grams. So this is our initial value problem. Let me just acknowledge that. This is our initial value problem here. This is our IVP. And this is the IVP that we wish to solve. Okay, this should not be too difficult. What we're going to do is, of course, use the separability. So if I divide both sides, I guess I should write this as ds dt equals 16 minus s over 2, and then multiply both sides by 2. So I get integral of 2 over 16 minus s ds. equals the integral of dt. Okay? So all I've done is move, first rewrite 8 minus s over 2 as a single fraction, giving it a common denominator. And then I divided by it to get this, and then integrate. It's the usual story. Okay. Yeah. Okay. So now we have to integrate this. Ew. So well, I'd just rather not think, I guess. So let me do u substitute. Oh, shoot, I don't want to. Okay, I'll think hard. I think it's -2 times the natural log of the absolute value of 16 minus s. Is that true? Well, to verify, let's take the derivative of that. So this is -2 divided by 16 minus s. But then we have another negative sign because of the chain rule, and the negative signs get married because a negative times a negative is positive, at least for a little while, in the United States of America. And so, yeah, anyway. And so we have this here. Yeah, this is right. And this is equal to t plus c. If you don't believe me, do use substitution, okay? Okay, cool. Now, what is c? Well, we can figure that out from the initial condition, right? Is this the way I want to go about doing it? Maybe what I'd prefer to do is divide both sides by -2, I guess. So I get negative t over 2. And c, there's no condition on it, so -2, or c divided by -2 is just c itself. And then I'll take an exponential. And then remember, exp of c is some constant, and then I plus or minus it, so I get 16 minus s is equal to, I'm just going to call it c, but now it's a multiplicative c out front, like this. And I guess I'm supposed to now subtract 16 and then flip sign. So I get that s is equal to 16 minus c times exp of -t over 2. Okay, that's my s of t in general. I haven't incorporated the initial condition yet. So if I want to use the initial condition, gosh, if I was better at doing things. Oh, look at what I can do. Wait, this is going to screw up your notes maybe, so maybe I won't do that. You know what? I will. You just have to deal with it. I'm going to take all this and pretend that I was really good at doing this, like planning my things out. I'm just going to move it all over here. Okay, now I can use the fact, continuing this way, that s of 0 is 32. I can use this fact now. So if s of 0 is 32, that means 32 is what I get by plugging 0 into this expression. So I get 16 minus c times exp of 0. But exp of 0 is e to the 0. That's 1. All right? So I subtract 16, take a negative sign. So I believe that c is equal to -16. Which means that s is equal to 16 plus 16 exp of -t over 2. Yeah. This is s of t. I should be very clear. This is the amount of salt present after t minutes. T hours. Minutes? Hours. Minutes. Right? The amount of salt present after t minutes. some things to note. When t gets very, 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 very large, because this is a, a exponential with a negative coefficient in the argument, it's going to go to 0. So this term is going to die in the limit, and we're going to be left with just 16. In other words, in the long run, the amount of salt present will be 16 grams. Now, this was totally predictable, right? And that's because in the long run, even though the initial concentration of salt water in the tank was, as we said earlier, 4 grams per liter, because we're pumping in 2 grams per liter concentrate into this, in the long run, its concentration is going to be 2 grams per liter. And how many liters are going to be in the tank in the long run? Well, that's 8. So how much salt will there be in the long run? 8 times 2, which is 16. Okay, very sensible. All right, that's way more than enough. I don't know if I went over time. I hope not, but appreciate you all, and thanks for watching. See you in the next one.